All right. Okay, I guess we can start here. Um, Good morning. My name is Harry Ricker. This is the Cosmology Discussion Group meeting for November 23rd, 2025. And welcome, everybody. Today, Ian is going to give us a talk, a presentation that should be interesting, and it's going to be about Sagnac effect, I believe. So go ahead, Ian. You're on.
Uh, so first, I'll have to share my screen.
Okay, there we go.
Can you see it now? Yeah. Okay.
Yes. Okay. So you need to,
The
one of the
photographs, the photographs are getting in the way probably. Uh,
you move them to the side.
I move them. Yeah, very good. Like that. Oh.
Okay. Full screen, I think, or a slideshow would be
Uh,
good.
well, what I'm proposing to do is I'm proposing to go through this Word file, which is written for people who have no scientific knowledge at all. But I have little red notes there. So note one there in red means I go to slide one. So I have slide one, which is more for you people, technical, in other technical slides, or maybe to expand what I'm saying. So I don't know if I have to make that the Word document bigger. I'll certainly make the well, I'll show you what this what the first slide is, just to indicate that. Here it is. I can speak to that maybe. And
And you go to slideshow mode.
yeah, is that all right, Jim?
Beautiful. Thank you.
Excellent. Good. Okay. It seems to be working. Uh, there's a banner there. Your screen sharing, I suppose. So maybe I'll use this first slide to introduce the situation, although Harry did summarize it in the calling notice. So about 3.5 years ago, I was invited to join a writers group, which basically meets regularly. They're mainly elderly people. I wouldn't say most of them are highly educated, but they're reasonably well read, and their writing capacity isn't too bad. But we got talking, and I'm the only scientific person, I suppose, in the group. And they said, "Why don't you come and listen to all our essays, and then you don't have to give out everything until the following session." So I did that, and I had some informal conversation with them because they were asking me about my background, and I don't know how it came up, but it came up that I'm not a mainstream scientist, and so I thought maybe I'd shock them with my first talk, and it was a bit of an exercise for me as well to try to explain to an unscientific audience how the experimental Sagnac effect disproves, or so I say, Einstein's special theory of relativity. So that's the first. That was the task. Now, what I've done for today, I thought that would be rather pointless to give to you people. So I have about 11 slides which I'll refer to, and some of them are technical, but I haven't presented those obviously to the non-scientific audience. So let's see, can I get this down now? Actually, those pictures are. I wonder, can I see? They're stopping me getting the. If I put it over that side, maybe. Okay. So at least I have the control here. So, I suppose, as I intimated, having listened to the eclectic presentations at my first attendance at a meeting of the Ballyroan Writers Group, that's the name of the group, on the 12th of May, that was 2022, my mind became flooded with ideas regarding possibilities for my own first presentation. But what was appropriate? I was soon guided by member suggestions to provide something of a scientific nature. So they had actually suggested that to me, I suppose, being thus rather complementary to other subjects covered, which were more in the artistic line. And by the way, I don't at all mind being interrupted. In fact, I think when I show the slides up, that may be a good opportunity, Harry, for people to come in and start asking me questions and maybe analysing it in more detail, because that's where the technical detail comes in. Anyway, this is more conversational. So, on further reflection, I decided to take the bull by the horns and start with some bold shock and awe. It's quite shocking, I suppose, if you make a statement like this, which unscientific people, have been led to believe that one mustn't question the infallibility of Einstein's theory. By endeavoring to explain in layman's terms, hopefully easily comprehensible, the essentials of some rather fundamental work in physics I have been engaged in for some years, which, if correct, will overthrow much of the currently accepted basics of that subject. It has been said that a man does not really understand his technical subject unless he can describe its essentials to the first person he happens to meet in the street. Einstein reportedly referring to any 6-year-old as his listener, and Lord Rutherford, quite politically incorrectly, to any barmaid at all. Rutherford achieved the first nuclear transmutation using a radioactive trigger as a source of alpha particles in 1917, popularly referred to as splitting the atom. And he was the supervisor of my late professor in Trinity College, Dublin, that is, E.T.S. Walton, who, along with Sir John Cockcroft, did the same with artificially generated and accelerated particles, protons, in 1932. So I think we can excuse his possible offence to modern sensibilities. Slide 2. Let me just bring that up now. Yeah. So there's a picture of the great man himself, with Walton on the left and Cockcroft on the right. So he's quite happy that they've finally appeared to transmute lithium into helium. Right.
Is that you in the photo, Ian?
Is this a joke, Jim?
Oh, well,
Are you serious?
the middle person, I thought maybe that was you.
That's Sir Ernest Rutherford.
Oh,
Yeah.
okay. Sorry for the, sorry, excuse me.
That's Walton, my old professor, and that's Cochrane. Well, Walton basically spent most of his life as Professor Erasmus Smith, Professor of Natural Philosophy in Trinity College Dublin. Cockcroft went on to become director of the UK Atomic Energy Authority in Harwell, and Rutherford, I think, died in the late 30s. But Walton says when he was talking about, there was a little cage where they had to go in to look at the scintillation counter. And he said, what's his name? Rutherford was a big man. Well, he was obviously big, but you can see he's a little bit bigger than Walton there. So it's hard for him to get into the little cage because he wanted to convince himself that the scintillations were of alpha particles. Anyway. Which Walton said he had a right to claim the capacity to identify, because not only had he first viewed them, but he had actually christened them alpha particles. Okay. So it is, by the way, paradoxically sometimes less challenging to explain some technical matter to non-specialists than to specialists, as the former, if the explanation concurs with their idea of common sense, are less likely to oppose claims that fly in the face of accepted orthodoxy than the latter, who are often subject to unconscious bias. In Tolstoy's words, I know that most men, including those at ease with problems of the greatest complexity, can seldom accept even the simplest and most obvious truth, if it be such as would oblige them to admit the falsity of conclusions which they have delighted in explaining to colleagues, which they have proudly taught to others, and which they have woven thread by thread into the fabric of their lives. I think many of us have probably come across that quotation before. So yes, I might say that I didn't really receive much hostility from the group, or even facetiousness. I'm almost expecting to hear that because maybe technical colleagues, engineering colleagues, would have been less sort of open to some of my views. They would have said, "Who do you think you are challenging Einstein?" So there's the paradox. Ordinary people who know nothing about science are perhaps easier to convince. So I then went on to say, enough said in introduction. Let us now cut to the chase. Among the myriad of scientific facts or so I claim, contradict the currently accepted basis of modern dynamics, the special theory of relativity, which I'll abbreviate as SRT, I shall concentrate on just one. Now, what have I done here? I've just tried to illustrate this a bit more as well. Okay, just a bit of Latin. Ab uno disce omnes. So from one you can learn all. From one example, one can learn all. And I quote here this outline from a scientific book written in 1935 by J.W.N. Sullivan, Science, a New Outline. Suppose we are at rest in what? And that we are passed by an observer traveling with half the velocity of light. We send a ray of light after him, which we observe to overtake him at the rate of 93,000 miles per second. Our statement asserts that this observer, when he measures the velocity at which this ray is overtaking him, finds it to be 186,000 miles per second. These statements are so opposed to common sense that they sound like sheer nonsense. Now, this large tome written by Alfred Rahely, Electromagnetics, in 1938, he quotes this and he just says, not only sound like, but really are sheer nonsense. Okay. So let's get rid of the slide for the moment. Go back to the text. I have a few slides when we come to the Sagnac experiments. Okay. This not only to concur with my present aim, so I'm giving one example. I could give myriad examples, but this not only to concur with my present aim at succinctness and lack of overburdenness, but also because of the evident fact that though one can never definitively prove the correctness of any scientific theory, no matter how many data it appears to agree with, it takes just one disagreement with such data to prove its falsity. So the one discovery I shall be here talking about is the so-called Sagnac effect, which is an effect that causes light rays moving with or against the rotation of a piece of apparatus to arrive at different times back to the emitter, which is also the observation point. Its discovery dates to an experiment of the French physicist Georges Sagnac in 1913, which he interpreted as showing the falsity of the earlier 1905 SRT of Einstein and the existence of a light transmitting medium or ether, Greek ether, from the root to burn or shine.
Can I interrupt here, Ian?
Please do, Jim. Yes.
This paper by Sagnac in 1913, apparently, which he, as you say, contradicts Einstein's SRT. Apparently, during that period of time, criticism of Einstein was allowed. That's what I'm asking you about.
Oh.
It seems like maybe that same paper today would be turned down by editors or journals.
That's a very interesting point. And if you look at the dates, because we frequently talk about the 1919 experiment, the Eddington experiment, which is claimed to have substantiated GRT, which really put Einstein into the arena as a personality, as a film star, effectively. And after that, it became, just non-new to criticize Einstein. So I think you've raised a good point, actually, Jim. And what I was going to say, I think lends further credence to that because Sagnac actually was aware of the 1905 paper. He had an assistant who co-wrote some of the papers. I've forgotten his name now, but they actually went out. They said, we're going to do this experiment to see is this whole special relativity business nonsense, which it appears to be, and also is there an ether? And they claim to have done that, to succeed in doing that. So 1913. And by the way, one other thing I didn't mention a bit.
And the editors accepted that paper, and it was published.
It was published in
Yeah.
Compte Rendu, the French. They had two papers. There are two papers actually. Yeah, Compte Rendu is published straight away. And you're right, because it's really, I would say actually post 1919 that well, I don't know about the paper being discountenanced, but I'll indicate some of the excuses that the modern mainstream make if one brings up this paper, and I'll try to demolish them actually insofar as I can. I only have a few technical slides, but anyway, I'll try to do that.
Okay, thank you.
Yeah, thanks for raising those points. I just want to mention one other point, which that actually reminded me of. There was a German postgraduate student by the name of Harris, Harres. I think it's Fritz, I think was his name, Harris, who actually appeared maybe in 1911 to have found this effect, the Sagnac, the different phases on the two rays going in opposite direction. But he wasn't looking for this at all. He was actually doing research on the piezo drag in crystals, in glass crystals, and light rays going through them when the crystal was rotated. But it appears that he wasn't aware of this actual fact in this way, but it appears he probably discovered it before Sagnac. Unfortunately, in 1915, he was killed during the First World War. He was in the German army. So anyway, just in case you come across Harris. Okay, so here's a summary for you people now. I obviously didn't put any of this in there because I have no visual aids for the writers group. But this was basically a schematic of the original Sagnac experiment. And the light comes in here, is bounced off mirrors. And then here it separates into R and T. So you can see my cursor. So the R one is going this way because it's the normal half silvered mirror. It's going this way. So this disc is going this way. It's going clockwise. So the R is going against it. It's going anti-clockwise. And then the T one is going with the disc, okay? And it's bounced off against mirrors. So it's an approximation to a circular traverse of this disc, the periphery of it. And basically any difference in time of transit should be when it's moving tangentially or at an angle to that. When it's going radially, there'll be no difference because they're both going the same way. So, for example, actually, they had a photographic plate there. That's what PP dash is. So this thing at the very end goes to a lens, and both rays T and R go here. So there's the detector, and there's no net effect here because that's going radially. So it could be back to here the same way. Okay, so they measured a fringe, and this is what the paper in Compte Rendu, which was published in French, and it's available in English as well, by the way, you could get it easily. I think it's probably available on the web. I think I got it in the British Library first in the 1990s, but it's available on the web now. They measured a fringe displacement in counter-rotating beams, the T and the R beam, and it was determined by the speed of the disk. So, for example, most of their experiments, they got about 0.07 of a fringe shift for a speed of around 2 revolutions per second, or 120 RPM. Now, so here's the interesting. The traversed path which is going at C naught. And I'm just keeping that C naught in because you know my proclivity for looking at dielectric media and putting a C M maybe in a medium and relating it to mu m and mu and epsilon m, the magnetic and electric properties. So C naught will be related to epsilon naught and mu naught. So the traverse path, which is going at the speed of light in free space, in vacuum. Now, here's the point. It varied in length as viewed from the lab frame, and I have a slide to show that in a moment. So maybe we'll discuss that in detail when I show this slide. But or the speed of light varied as viewed from the rotating frame. So the common excuse used is, oh, there's a different amount of length that it has to traverse. So the ray that's traveling with the disk, well, the detector is moving away from it, so it has a little more to traverse. And the ray which is moving against the rotation of the disk is approaching this thing, and therefore there's a little less to go. But see, if you have an observer on the disk, well, there's no variation in the distance between the detector and the observer or the emitter. So that's constant. So the speed must vary. We'll come back to that perhaps in a moment. I didn't mean to zoom in at that actually so much. That's better, yeah. So when I show the idealized diagram with the round system, now, if you do a simple calculation, which I'll give you the equations for presently, you get, well, I call it delta t minus. So the difference between the time to traverse it when it's opposing, in other words, the R ray, as against when it's moving with it, the T ray, is 4. Well, I say approximately there because actually we yesterday we were talking about the gamma factor, and I know Jim said, "Oh, it's just dismiss it all." Well, I thought it was a fudge, but I used the gamma factor. Actually, the gamma factor comes in here, and we're just approximating it to 1 because the speed is so slow relative to the speed of light. So that's why you have an approximate sign there. But it equals 4a. A is the enclosed area. Here would be S. You see the surface area, closed area by the traverse of the rays of light. Omega is the angular speed of the disk, and C naught squared is the speed of light. And you can get the phase from that by, using the wavelength and the speed multiplication. Now, so that's basically the Sagnac experiment of 1913, which was published in Cowan. And I just mention here, because I have it included on the slide, that and I probably have mentioned this before, but Sagnac found out some other things. So contrary to, I think, what a number of people who've accepted the Sagnac experiment, but claim that the light does take on the spin of the disk, that is not so. There were, again, two Frenchmen, Dufour and Prunier, who in 1942 produced a paper. They did the work just prior to that, whereby they repeated Sagnac experiments, but intermediate between the source of the light and its reception by the detector, the photographic plate. They did a lot of things. They bounced it from a mirror onto the wall of the laboratory and maybe onto the ceiling of the laboratory and came back, and they tried things like that. It made absolutely no difference. So the only way to explain that is that the light was traveling in the frame of the laboratory or within the ether frame. And if you postulate, as I do, by the way, a Stokes ether drag with regard to the revolution of the Earth around the sun, well, what's giving rise to that ether drag is either a gravitational or electromagnetic effect. maybe they're both the same, or maybe a combination of the two, because of the very great mass of the Earth. Here you have a very small disk, so it doesn't drag the ether at all. And similarly, when you have the rotation of the Earth, the daily diurnal rotation of the Earth, that doesn't drag the Earth ether either. It actually moves through that, and we can indicate some experiments to show that, the Michelson and Gale, which I'm coming to in a moment. But the Dufour and Prunier experiments are even less well known than the Sagnac one, because the Sagnac one is sort of known and dismissed, but the Dufour and Prunier one are not even known. And it appears that these papers didn't come out. Now, they were written in Paris in 1942, when Paris was under German occupation. So that might be one reason why they didn't come out, you know. But after the war, they didn't come out either. So it's quite a curious situation. Anyway, I'll be coming back to that, but I think I've only just to introduce you to the one slide before moving on with the paper. So, of course, the ordinary people don't know any of these details. They would have asked me to stop, actually, had I done that, because I think on one other paper I just even verbally mentioned a simple formula. They said, no, that's beyond us. We couldn't understand that. So I'm keeping all these technical things only for you people, audience. So SRT claims essentially that light speed is constant and independent of the motion of the observer, not having a medium of transmission that can be used as a frame of reference, unlike sound waves in air, for instance. Now, in 1925, physicists Albert Michelson and Henry Gale constructed a light circuit of almost 2 kilometers perimeter in a cornfield in Clearing, Illinois, just outside Chicago City, and successfully measured the rate of daily spin of the Earth using the Sagnac effect. Sometimes you'll see Michelson, Gale, Pearson, because they had actually a considerable amount of help from another operator there, Pearson, but it's probably more frequently just referred to as the Michelson-Gale experiment. So I have 3 slides on this, so we can go into, and you may want to quiz me here a little, 5, 6, and 7. See, I left it at that for the non-scientific people. Okay, what's 5? Yeah, okay, well, this just, a lot of you know this already. The Michelson-Gale experiment in 1925. They measured a fringe displacement, which averaged 0.230. There is a bit of a criticism here in that it was varying all over the place, and that is an average of quite disparate values. But anyway, in counter-rotating beams through a piping some 1,850 meters in perimeter. So the light is coming in this way, and one goes that way, and one goes the other way. This small circuit, they can block that off and have it going just around this small circuit. That's what they refer to as a fiduciary circuit. So the same equation applies where it's dependent upon the area. Hence, you needed something like 2 kilometers perimeter to get a reasonable effect. This has almost zero area, so they wanted to make sure there was no fringe displacement when the counter-rotating beams were combined there. So determined by the speed of the daily rotation of the Earth at this site, which in Clearing, Illinois, was 350 or is 350 meters per second. And again, exactly, excuse me, in the as in the Sagnac case with the disk, the traversed path, again, the ray was progressing at C naught, a speed of C naught, varied in length as viewed from outer space. So again, if you could get away from the Earth's rotation and look at this from a stationary observation point, let's say an absolute frame, well, you would think the amount of distance that the ray has to traverse would be increased or decreased depending upon whether the ray is going with the spin of the Earth or against it. But if you're on the Earth, in this case, the speed of light must vary because there's no difference in the distance that the ray of light has to move. They're all fixed on the spinning Earth. So the speed of light must vary as viewed from the light frame. Now, if you do just a little mathematics, you get the same formula, but here the sine of the phi is the latitude, or the cosine of the colatitude, because it's the projection of this experimental setup onto the plane of the equator around which the Earth is spinning. So you get 4a omega sine phi over c naught c squared. Now, again, just one other later experiment which I'll refer to here. Um, we said this yesterday actually. Why MMX? Why not MMX? But why Sagnac? Why does MG show up a positive value and MM doesn't? Well, um, actually, the MMX type experiment is a second order effect. And if you look at V over C and you square that, it's very, very hard to get accurate values there. This is a first order effect. It's omega is V. Omega is V over R. So it's V is the speed. It's a first order. It's not V squared over C squared. It's V over C, or V over C squared here. So it's a first order effect in V. Now, however, in 1979, this may be the first time this was done. I believe these things are being done every day with counter rotating masers, but they were the first to do it in Brie and Hall in 1979. They had which is the analog of the original 1887 Michelson-Morley experiment. These are counter propagating masers, and they actually indicated the rotation of the Earth with such an apparatus, because they were trying to prove that the result was absolutely zero, which is what special relativity would demand. And actually, they got a frequency difference of something like 17 kilohertz, I think it was. And they dismissed it. They said, well, that was obviously noise. There was vibration from they were I think they were in a cellar below a motorway or something, heavy vehicles going on top. So they dismissed it as a spurious signal. But Aspden, the British physicist, analysed this somewhat later, and he found that actually corresponded to the 350 meters per second traverse of the Earth. So that sometimes is claimed to be the first time the Earth's rotation, as distinct from revolution, was measured using Michelson-Morley apparatus rather than, say, a Michelson-Gale. The Michelson-Gale apparatus did show up the speed of the Earth in 1925. Now, let me see now. Okay, so
You have
this
4 minutes. 4 minutes.
Oh, do I? Well, let me see. It's taking longer than I thought, but that's because the slides, I'm talking more of the slides, and I'm getting welcome interruptions. Well, it's mainly Jim, but thank you. I want that. I wonder, should I start or should I just stop and maybe continue at the next session? What do you think, Harry?
Why don't we stop here, and
Yeah,
if
yeah,
anybody's got any questions, that
indeed.
way you won't get cut off.
Yeah, perfect. Because the slides, you probably need not to be cut off when we're discussing those.
Well, so far, I'm very interested. You provided a lot of information. I hadn't really heard it all put together before, so it's helpful from that point of view.
Okay, that's good, because in my case, it was a bit of an exercise. I said, can I try to explain in layman's terms something about this, just to get the interest of these people piqued. And then I said, well, since I've offered to give you a talk on it, I need to go into the technical details, and that's what I'm trying to give you. And I'm delighted if I'm telling you something that you didn't quite know about this. I mean, you're all familiar with the basics of it, I'm sure.
So the group that you were of laymen that you were talking to, did they appreciate your talk?
Yes, I think so. When I'd finished, there's a lady there actually who writes minutes, and she's very good. She sort of goes into more detail than the original essay would be. But she said, see, there's a mental block with non-technical people. I feel this strongly. But she said, I couldn't summarize that in. Would you give me a copy of your paper? So I gave her a copy of my paper, and then she wrote minutes, just very, 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 very roughly. But yes, they were quite appreciative, and I think awe was probably an appropriate term because I thought they were in awe. They're used to looking at all these popularizers of science, um, like Neil deGrasse Tyson and all that. And I'm later on you'll see that I'm sort of attacking them and saying don't believe what you're hearing on the common media. And by the way, I think Jerry's not here, is he? The reason I ask is Jerry. Jerry's an interesting thinker. He seems to get cut to the chase, but he has a bit of a hang up, I would say, if I may, about the Sagnac effect being explained by the traversing of the differing distances. Now, that's the common excuse given.
Ian.
Oh, Jerry, are you there?
Yeah. I wrote something in the comments, and I was gonna read it or talk about it in the next session because we're almost out of time.
Yeah, I want to talk to the because I apologize and thank you. I'm speaking.
No, that's cool.
About you. You're in your absence. I thought you're there, but I haven't really got down to discussing that with you, and I hope maybe today we can have a bit of a discussion because, and I want there is something in what you say, but one has to look at it in a particular way. The Wikipedia just says that it can be explained that way, and I dare say AI it does as well. Now you might be glad to hear that I have not consulted AI for this, and nor do I have any intention of wasting my time or your time because I know what it's going to hash up.
Well,
So we'll deal with the first principles when I get to the slide. I think it's the next slide.
okay. Well, I've actually revised my viewpoint. I
Have you?
wrote to you on Discord explaining
Oh.
you probably haven't been there in a while.
I missed that, I think.
Yeah.
Okay.
Okay, we're coming to the end. Cut off 20 seconds or so.
Okay. I'm just trying to see, can I see that? Okay, we'll be cut into the next one. I have to go through the sharing system again, Harry, do I?
Yes, I think what happened was when we changed to the new meeting, it started a new chat.
Okay. Yeah, so I haven't seen Jerry's chat, but he can tell me about it when we get to the point. I think it's the next slide. Send request. And there's James, our speaker from yesterday. I was claiming to be Louis the 14th. C'est moi. And Jim is here. Yeah, it's great. Vladimir as well. Okay, so, and now I have to share my actual screen. Share. Now, okay. So what I want to put up is that.
Here we go.
Yeah. So I think I was on slide 6. I have 5, 6, and 7. So let me see if we're in that's this. That's 6. Yeah.
There we go.
Okay. Oh no, I have 2 slides we want to talk to. And I invite you to quiz me on these. So here's an idealization of the situation, frames of reference. So we have the disk here, and we have a perfectly circular traverse by the disk is going this way. Well, here's the same when it's stationary. When it's stationary, they have capital omega is the red ray is going clockwise and the blue ray is going anti-clockwise, and they meet back at the same place. But when it starts moving clockwise, well then the red ray when it gets back to here, the starting point, the detector will have moved a bit further. So it has this extra bit to traverse. And the blue ray well, the Blu-ray is going this way against the rotation. So the rotation is coming towards it to meet it. And it has that less distance because it meets it there before coming back there. Okay. So if R is the disk radius and we say delta L, they use capital L here. I've just got the distance detector has traveled prior to ray contact. So that's what I'm calling that. Now, so there are two ways of looking at this. They're getting the same equation as I do, the 4 area C naught. The distance is C naught times what I call delta T minus. So it's just an extra C naught in there. But we can analyze it in 2 ways. We can analyze it in the lab frame. So what we do there is we say the circumference of this disk, twice pi r, plus or, what have I done?
Uh-oh.
Yeah, it's
There
all
we
right.
go.
Yeah, I must press a button. Plus or minus delta L, depending upon whether we're using the red ray or the blue ray. Now, that distance, that net distance which it has to traverse, divided by C naught, is the time that the ray takes to go from its initial emission to its final reception, if you like. Now, if you divide that by C naught, you say it's moving at C naught in this because the disk doesn't have any effect on the speed of it did. By the way, if it did, some people are, oh, it does. It does. Funny enough, I had a discussion many years ago with one of the geocentrists, believe it or not, Robert Bennett. Yeah, that was his name. And his analysis was very similar to mine, but he was adamant that the ray of light took on the spin of the disk, and I couldn't convince him otherwise. But if you work out the equations, there would be no Sagnac effect because that would compensate. If the light which had we're traveling with the disk, which has a greater distance to traverse, we're actually also increased in speed by the disk. Well, then that would cancel out, and similarly for the other disk. So anyway, if you go back to this equation, you divide it by C naught, and Sagnac experiments have proved already that it's going at C naught. Well, that's the time it takes for the ray to traverse the distance from its emission to its reception. And we can call that, there are 2 cases here, plus or minus, the red or the blue ray. We can call that delta T plus or minus. But we can equate that to the amount that the disk traverses in that time, which is simply that actual difference in distance divided by V or omega r, keeping it in terms of the angular speed. And if you just do that by simple algebra, I haven't actually done it. Sorry, this is going. You can evaluate delta T minus, which is the difference between the two, the delta T plus here and the delta T minus. Well, I call that a smaller minus. That's the net. So you get you evaluate that. Now, however, if we look at it in a disk frame, if we have somebody who's stationed on the disk, well then, and if you forget about SRT, the time is just excuse me. The greater time it takes when the speed is C naught minus V. So it's the length divided by the speed, and you subtract that from twice pi r, the length, over C naught plus V, C naught plus omega r. Now, the interesting thing is I haven't actually done the 1 or 2 lines of simple algebra. I haven't done it here, but if you do it, it leads in both cases, as it should. There should be no difference. Reality is reality. It doesn't depend on the frame of reference, so I say. So you get the Galilean composition of, I forgot to get rid of this actually. The Galilean composition of speeds. So the delta T minus is proportional to 1 over C minus V minus 1 over C plus V. And if you solve either of those equations, you get this correct value. You get the same value. So that's an algebraic way of looking at it, that from the point of view of somebody on the disk, the speed is changing. And from the point of view of somebody outside the disk, the distance is changing, delta L. So to say that the distance is changing and the speed is the same, that's true in the laboratory. But on the disk, the distance is not changing, it's zero, and the speed is changing. So it's a bit like looking at a ray of light going in a horizontal direction, and you have a motor car. Well, forget about a ray of light. Say it's another motor car. Two motor cars are approaching each other on a highway, and you're looking at you're looking at the car, which is the observation car. It's moving towards this object. The object may or may not be moving. Let's take a simple case that it's a telegraph pole or something. The car is moving towards it. Well, that is true that from the point of view of somebody looking at it from the outside, the car is closing in upon the telegraph pole. So the distance is changing. And if the car is going the other way, away from the telegraph pole, the distance is increasing. But it would be ridiculous to say, therefore, the relative velocity is the same as if the car were stationary. The car is moving towards this. And if you have two cars and they're moving towards each other, you have to add the two speeds. And if they're moving away, subtract them. So we can come back to the slide if necessary, if you need to look at that. But you need to look at it both ways. And the mainstream, well, if you solve that equation, you get that. You get the same value. So you can see straight away that it's just C naught minus V and C naught plus V. But the
But
mainstream,
in the mainstream, they would say there's no C plus V or C minus V.
that's right. But they accept this formula, Harry. And if you solve that for delta T minus, you get this equation.
Right.
So I don't know how they
And
explain that.
another thing about the mainstream is that they claim it's all a rotational effect. It's not.
Okay, that is the other good point, Jim. That's correct.
And that it depends on the area, where the formula does come out to show an area, but that's just a different way of looking at the equation.
Yeah, quite so. You're right there. You've looked at that. So in other words, if you substitute for L, which is the length that it traverses, 2 pi r, you get a value. Now, if you say that area equals pi r squared, and you eliminate r, that's where the 4a omega over c naught squared comes in. But actually, it appears that you have to be a bit careful there. That's a nice way of expressing it, where you have a circular or a nearly circular traverse. If you have a very irregular traverse, it seems to be that it's safer to keep L in and forget about twice pi r and all that. So it's just a handy way of doing it if you have a circular system. And the original Sagnac experiment is approximately circular. Okay, so this is how I'm trying to demolish the common argument which is given, and you've given the other one, Jim, to say that Einstein doesn't apply to circular; it's a non-inertial frame. Well, we'll have a couple of things to say about that. One is it's funny how Einsteinian dynamics, which seems to be a refinement of Newtonian dynamics, breaks down suddenly when you have a slight departure from inertiality. But Newtonian principles, which I'm using here, I'm using Galilean composition of speeds and Newtonian ideas of velocity and space and time, they apply perfectly well. So I'm not sure if it's good enough just to say, no, it doesn't apply. And of course, you can make if this disk has a radius, well, you can make that disk as great as you wish, and you can approach the straight line system. And we actually have evidence for that. We'll be coming to that in a second. But before that, I just have another thing. I just look at the symmetry of this. I say all the preceding. Well, in this case, I think in an earlier presentation, I was looking at Romer's experiments, and I put that in as well. I lumped that in as well. But I'm just talking about the Sagnac effect. And I say all the preceding apply for observer motion relative to a static source. But C naught is constant if the source itself solely moves. So here's something that also the Sagnac experiment proved. It actually proved a number of things. Proves three things. It proves the variation of the speed of light with respect to motion, where the ether is not dragged. It shows that the speed does not take up the speed of the disk. It's too small to have any influence on it. But it also shows that the speed is constant if the source itself only moves. Because if that were not the case, well, as I say, there'd be no Sagnac effect. Or there'd be some incalculable Sagnac effect. What is actually happening is the from the laboratory point of view, or from the ether point of view, the source is on a moving platform, and there's no ballistic effect. It's still traveling at C naught. You assume it's traveling at C naught, and you get all the correct values. You get the correct fringe shift and so on. So I often point out that in the 1905 paper, the second postulate, as it's stated in Einstein, is that the speed of light is independent of the speed of its source. That's what it actually says. Those are the words. And actually, that's correct. But so what? It's a truism, and it's true for all waves. And it manifestly does not imply that the speed is constant for the speed of the observer. And because of the symmetry which is imposed upon the Lorentz transformations by the Einstein idea, if one moves, it's only the relative velocity that's important. So if one moves, then and the other remains constant, it's the same as one remaining constant and the other moving. Well, that's manifestly not true. I've shown that by looking at the which I think Jim mentioned yesterday as well, actually, James rather, the aberration of light, but it's also not true. So the way Einstein first expresses it is correct, but then it's extrapolated to an incorrect statement. So Sagnac and Michelson-Gale experiments are analogous regarding Galilean composition of speeds. So if Galilean composition of speeds there, delta t minus is proportional to 1 over c minus omega r minus, so difference c naught plus omega r. So we were talking a lot about transformations and why the Galilean transformations are not sufficient. And maybe, although many of us look at it in a similar way, we mentioned Stefan Gift and also we were talking about it, James's James Archon's ideas, and we were seeing there's a lot of commonality. I think there's a lot of commonality, but we have some fundamental differences. But one difference which I have, I'm a bit of an advocate of the Galilean transformations, and I'm going to maybe delve a little more into that. But before that, 7 is the last slide I have before going back to the text.
All right, Ian.
Yeah.
We got questions.
Go
Go ahead,
ahead.
James.
I'll just make an observation, because you've been slightly, I hesitate to use dogmatic, but your Northern Ireland compatriot Walden wrote a book on wave and ballistic theories of light, and he incorporates the Sagnac effect into a Ritzian sort of worldview, but he doesn't give the maths. So you've actually said, oh, the ballistics theory doesn't work for the Sagnac effect, but he seems to think it does. So I'll just point that out as a possible. It might be to do with moving mirrors and some jiggery pokery you get that the ballistic theory is allowed.
Who was that? Waldron. Who was it?
Waldron.
He wrote a thing called the Wave and Ballistic Theories of Light. It was written in 1977. He was a very enthusiastic supporter of the ballistic theory of Ritz.
Okay.
I'll just point that
Okay,
out as
so
Yeah, I need to look at that a bit more. Yeah, I have appeared to be a bit dogmatic. One can be when one is speaking, but please take
no,
everything.
that wasn't a criticism. It's just an observation. So
Thank you. Yeah.
okay, he prefaced my question, so I'm looking for a more definitive dogmatic answer. So you're saying that you think these experiments that you're talking about do not support the ballistic or the emission theory of RITS. Is that
Yes,
correct?
I do, Harry. Yes.
Okay.
And if I were asked to justify that, well, I would say the original Sagnac experiment, if there were a ballistic effect, I think there'd be no Sagnac effect. Now, we'd have to look into that in more detail, but I think it's equivalent to the idea that the spinning disk takes the light takes on the spin of the disk and adds it to its system as if it were, a particle or a cannonball, which is being transported on a moving platform. If that were the case, well then, do you see? I don't know if this explains it, but Harry, the ray of light which has a further distance to go, this delta L distance, because of it's moving with the spin of the disk. Well, then that would take on an additional speed of the disk, which would compensate for that delta L. Or similarly, the disk which is going in the counter direction, the detector is coming to meet it. So it has a smaller distance to travel, delta L as well, let's say. But that speed would be diminished because presumably the RITS idea, it would encompass a counter ballistic idea as well. So in other words, if you have a platform which is moving in the opposite direction to a cannonball which is fired from a cannon resting on that, you have to subtract those speeds. So I maintain that those would cancel and you'd get no Sagnac effect.
I
Would
think
it be,
that's okay, go ahead.
I don't know if that's revolutionary. I don't know if that's been said before or if it's just my own idea and would have to be looked into. But I claim anyway that the Sagnac effect proves a number of things. It proves that the speed of light is not constant when the detector moves. It proves that the spin of a small element, material element such as a disk, does not have any effect on the light which is being transmitted upon it. And it also disproves the RITS ballistic theory that a light must have its speed added to by the platform on which it is moving.
I have two questions, if I may. I can't help but think, what if this revolving platform was perpendicular to the plane of the equator of the Earth? And up there in Europe, it wouldn't be necessarily perpendicular to the floor of the room, but what if it is changed in angle so that it's perpendicular to the plane of the equator of the Earth? Would such an experiment or measurement be relevant to exclude or include any of these possibilities?
Yeah, I think it would. I mean, the formula is that it's proportional to the sine of the latitude. Now, in that case, you're taking a latitude of 90 degrees. So you'd get the maximum effect, I dare say.
Okay. My second question has to do with what is the plane of the rotating apparatus that's used in navigation today?
Yeah, okay. So that's a good point as well. You've raised a number of points, and I'm delighted you have done it, which I'm coming to. What
I'm just trying to sort
Yeah.
all of this out because
Yeah.
over and over it seems like you're saying we get the same equation if we look at it this way or we look at it that way. So that as someone who doesn't think about this every day, I'm trying just to sort it out in my mind.
Yeah. By the way, I'm just thinking of the formula. I'll come to that in a second, but I think that's incorrect. I think you get the maximum value when it's parallel to the plane of the equator, and you get zero when it's perpendicular. So I'll just have to think of that because it's the cosine. That might be the colatitude which has come in there, the sine. I think it might be multiplied by zero.
When a Sagnac apparatus is used in navigation,
No,
it is somehow the rotation is somehow
yeah.
fixed.
So what they do, yeah,
They have
indeed.
it in three planes, don't they? All
I'm just going to say
accelerometers.
that, Jed. You've taken the
Yeah.
words out of my mouth. Yeah.
Sorry.
So in other words, what they have is they have three
It's gimbal.
fiber optic, three not
Perpendicularly.
fiber optic, but three. What do they call it? Gyroscopes, laser gyroscopes, which rotate about three perpendicular axes. So. So if you have an axis, if you imagine just from our point of view, Cartesian coordinates, if you have a sort of X, Y, and Z, if you have, say, the perpendicular axis to us, up and down, any rotation of a gyroscope, a laser gyroscope about that will determine or measure the yaw of the plane. Now, then the second axis is the horizontal one. Well, the horizontal one across the motion of the aircraft, say, and the third one will be the horizontal one in the direction of the motion. Now, the one in the direction of motion, that will measure any roll of the aircraft. And the one across the direction will measure any pitch. So that's it, three axes, and each of those will measure any variation in or any rotation of the aircraft in around the particular axis.
Thank you. It seems to me then that if this is a practical device that is used, and lives and resources like the cost of the airplane and so forth are involved here, it would seem that the interpretation that makes this work is hands down the winning interpretation.
And you see, that's precisely my next paragraph in my paper. So you've almost read my mind. You know, you're thinking in the same way as I am, Jim. That's what I actually said to these people. So we're coming to that because I think slide 7 is the last of the theoretical ones, and we can come back. No, there are two more theoretical ones, but we can come back to those. But if you'd like me, let me just see now. Jim has raised the point that is my next point.
And let's proceed from all this is easily explainable.
Yeah,
So we're back to
exactly.
your talk.
So I think the next point.
But we've gotten so far away from the original theme of your presentation that
Yes, yeah, but there's no harm because at least we're drilling further into it. So what I do is I talk about the mental juggling and the special pleading, and then I come to the very point that Jim has just made, the practical application. So all this is easily explainable using Newtonian dynamics, which is what I said earlier, but seems quite to contradict Einsteinian, or at least requires some not insignificant mental juggling and special pleading, which have been evinced by those over the years who have wished to save SRT. So I'll just mention one other thing to you. I don't have a slide on this, but Langevin said perhaps time changes by plus or minus 2a omega over c naught squared. He couldn't bring himself to say that it's the velocity which changes. He says maybe the time of these two rays changes. That'd be one explanation, ad hoc. I had never, and then I said to the people, I had never heard of these experiments as an undergraduate, nor do they appear at all in the textbooks. There are articles on them in Wikipedia, but they are subject to the special pleading and saving endeavors that I've referred to. So they do give some equations in the Wikipedia, but they rely upon the difference in distance, which we may talk a bit more, Jerry, in a moment, and they rely upon it not being inertial and so on. And as I say, you'll probably be delighted that I shall not be referring to AI today, because I'm sure it's putting up the same rubbish. Now, this is the point that Jim started on. All of us, I am sure, have had occasion to travel by modern jetliner, and were confident that the navigation systems employed would reliably take us to our destination. Modern aircraft do not employ the older mechanical spinning gyroscope to detect three-dimensional motions and make the requisite corrections, but what are called ring laser gyroscopes, which do so by sensing the time difference between laser beams traversing optical fiber circuits in either sense, thus permitting the accurate assessment of any pitch, roll, or yaw of the plane, as we just talked about. The Sagnac effect is central to the operation of these devices, which, or so I say, would show no transit time difference and thus not work where SRT correct. It is also worth pointing out that a Sagnac correction for the spin of the Earth has to be taken into account by GPS devices. Westward signals will exceed eastward in speed on the surface of the Earth. By the way, just before I get to slide 8, another quick fix, and I think even bodies like the ITU have sometimes referred to this in some of their publications. They say, oh, time dilation. Well, if you work out the difference between time dilation in, say, a GPS satellite and the Sagnac effect, it's orders and orders of many, many orders of magnitude. The time dilation is only a minuscule fraction of it. So that doesn't wash either. But let's have a look at slide 8. Let me see now. Yeah, it is. So I've just said that GPS employs the Sagnac correction for Earth rotation. Now, Kelly, A.J. Kelly, Alf Kelly, in his book said that he wrote to the ITU, the CCIT at the time, the telecommunications one, or maybe it was the CCIR, and he said he pointed out in one of their publications they said this is a relativistic correction. And he said, it's not a relativistic correction in GPS. It's a Sagnac correction. And you're mistaken. So he actually got a reply from the chairman of the committee. And he said, oh, a bit like what AI would say. He said, oh, maybe you've got a point if you look at it that way. But it's all relativistic at the end of the day. So he got the mealy mouth. Anyway, now, and then the Wang experiment, Wang and his colleagues at Alia, 2004, have demonstrated, what am I doing? Have demonstrated the linear Sagnac effect with conveyor and fiber optic gyroscope. So here you have a conveyor which conveys this thing in this direction, V. And you have a fog fiber optical gyroscope. So you have it fed in. See, it's very sensitive, this. It's fed in to go against the motion of this track. And and also the other one goes... So this one goes with the motion. This one goes against it, and then it's fed back and analyzed. So they got results. They're very interesting papers, and I think I've told you before that I have been in touch with Wang, Ruyong Wang, and because he got in touch with me first actually and asked, could the CNPS write to the CCIT or CCIR, whatever one, any the ITU, telling them that since the speed of light varies on the surface of the Earth, it's a moot point to take it as constant so on. And I just wrote back. I said, well, I'm sure they would say that it's relativistic, and maybe they'd say in outer space they take C note. But I said, would you give us a talk on this, a Saturday talk? And he declined. I'm not quite sure why. He said he was very happy to keep in touch with us. If we have any questions, we could speak to him and so on. But anyway, if you do the analysis here, you get same basic equation with the C naught plus or minus V, 2L V C. No, sorry. L is the perimeter. Well, remember in the circular case, we substituted twice pi r for that, and that's how we got the 4 value in there. And the pi, the a got rid of the pi because pi r squared and so on. So it's the same. It's exactly the same thing. So that demolishes the argument that you must not even speak about this because Einstein didn't talk about circular transit, non-inertial transit.
That's because these are linear motions.
Yes, correct. And
Okay,
the
we've
only
got 7 minutes.
okay, well, I might be able to finish now. I'll go back because unfortunately I have one or two theoretical slides, but I'm almost finished. 8, okay. And now, so if I am correct, I appreciate that this casts an unwelcome shadow on the propensity of mankind, not excluding those engaged in ostensibly evidence-based science, to form consensuses that once formed or adhered to generally, perhaps often quite unthinkingly, independent of the evidence. Not only are professional and academic specialists thus highlighted in what can be a disappointing light, and here's my shock and awe again, but popularizers of science such as Brian Cox, Neil deGrasse Tyson, and Michio Kaku are, despite their significant professional credentials, often, not to put too fine a point on it, speaking through their hats. Now, when I first discussed Harry, I thought I'd finish all this in one session, but I have 2 more slides here. So, and you forgive me, they're a little theoretical. I thought I want to impose them upon you, just to indicate a bit more about the Galilean transformation and my ideas. Yeah.
Take your time, Ian. This is a great talk.
Well, thank you, Jim. Thank you.
Very good.
So again, I say, and this is one of my problems, and I think you actually had this as well, maybe more strongly than I did, about transformations being the answer to everything. They're really just a quick fix. Well, let's look at what causes these things. Now, if you analyze total derivatives, which are used in fluid dynamics, and if they are used by analogy in electrodynamics, including they provide a wave equation, including a convective term. So you have the Laplacian of value. It could be, it could be a property of a fluid like the pressure or something like that, or the density, or in electrodynamics, it could be the electric or magnetic field intensities. And you get 1 over c squared. And then you get this convective term, the dot product of the velocity vector and nabla, and they're in the 4 dimensions. And I say this obviates the necessity of using Lorentz rather than Galilean transformations to preserve invariance. So this is why I'll show you why. And in fact, James referred to this yesterday, I think. This gamma factor coming in, and I refer to it as well, the c squared minus v squared. This is why it comes in. But we don't need Lorentz to bring it in. I'll show you how it comes in from first principles. And thus, the simple 2-speed addition, if you have a motor car going in one direction, v1, the other v2, the relative speed is v1 plus v2. Rather than the Einsteinian one of v1 plus v2 divided by 1 plus v1 v2 over c naught squared. That formula is necessary to preserve the constancy of c naught, because if you substitute such a value, for example, if v1 is c naught plus v2 is still equal to c naught. So I think in a previous talk I said that you have a very high price. If you say, look, I want the wave equation to be invariant, what transformations are needed? Well, then the Lorentz transformations will do that. The Solari transformations will not. And I think, if I may speak for Stefan Gift, he says, well, why should it be invariant? But the Solari transforms concur with the experiment. That's his argument. But I say, okay, Lorentz transformations do render the wave equation invariant, but it's a very high price you have to pay. The price you have to pay is that there's no c naught plus or minus v. It's c naught. So just my one equation, a bit of mathematics here, just to show you the c squared minus v squared thing. I use the Stokes notation. I have the partial differential. Sometimes it's given with capital D, lowered scale, and you get that. And if you substitute that in the Maxwell-Hertz equations, in other words, where you have a partial delta by delta t, you have a capital D by dt in all the equations, both the Faraday type equation and the Ampere equation. You get that. I haven't put I've just put the operator in. I mean, you might have E or H there, but it's the second derivative, the second total derivative of the C0 grid of the Laplacian. Now, just for simplicity, we take, without loss of generality, we take a planar case just in the x direction. And we get
You're
that.
not going to make it. You got 2 minutes. You're going
Okay.
to get cut off.
Well, shall I come back to this? Shall I leave it now? And
Just do as much as you can, and then we'll come
okay.
back.
Okay. So just to expand that out, and here you have the c squared minus v squared coming in, and we just put it in terms of c naught plus v naught. This is all that simple algebra naught, and what you get is you get the same wave equation with c naught plus v, c naught minus v, and the solution is fx c naught plus vt, fx minus c naught minus vt. So that's the most complicated bit that I'm dealing with, and it's a justification, I hope, of my proposal that the Galilean transformations without any LLT, with any LT, with any ST will work, provided you use these total derivatives. Now, I'm nearly finished actually, but I think it'll go into the next session, because if I stop that and go back to the text, no, I have one more slide at the very end, I think 11. So it'll probably be cut off, Harry. To conclude, well, it's an artistic writers group, so I put in a bit of that. To conclude, I should like to recall the couplet in iambic pentameter, composed by Alexander Pope as his epitaph for Sir Isaac Newton, who died in 1727 and is buried in Westminster Abbey. Nature and nature's laws lay hid in night. God said, let Newton be, and all was light. To which Sir John Squire wrote in 1927 the reply, it did not last. The devil howling, ho, let Einstein be. The next session now. Okay. So the only thing is, for 1 minute, Harry, I have to share this thing again, I suppose. I think you heard Sir John Squire's reply in 1926 was, it did not last. The devil howling, ho, let Einstein be, restored the status quo. So things were not simple and light after that. So here's the end. Well, I presented a paper on my physics research to the 8th International Scientific Conference on Space-Time and Gravitation, held in St. Petersburg, Russia in 2004. I think that's probably partly responsible for my getting involved with the NPA at the time and so on. And sitting in my hotel room the evening before presentation, came up after some contemplation with the further updating couplet. But do not fear, though this confounds all men, quite soon we'll find all things come clear again. And I think I finished that with the 11th slide, which is, well, just repeating it, saying, I say, my dogmatic self says, as for other wave motion in a medium, the speed of propagation of light is independent of the motion of the source, but not of the observer. And this has been well established experimentally. And all this is consonant with analysis using classical theories of dynamics and the kinetics of fluids.
Ian, I'm sorry.
Okay, Jerry. I'd just like to say thanks very much for listening. I hope my trying to meld a general statement to non-scientific people with some more detailed background to you people has not been too unsuccessful. Thanks very much.
Well, it's been very good, Ian.
Thank you.
I appreciate it.
I wish this talk could be given to undergraduates. Physics undergraduates.
Well, I'd be delighted if I was invited to, but yeah.
Ian, Which experiment proves what you had just said, as far as when the observer is in motion, that C isn't invariant? Which experiment is that?
The Sagnac experiment, Jerry.
Oh, okay. I've heard you refer to that many times. I didn't know that that was what you're referring to. Okay, cool.
Yeah, yeah, yeah.
Well, his whole talk is a theme on this, what the Sagnac experiment leads to, and it also leads to the gyroscopes and the Wang experiments as well.
Well, the light source as well as the reflect sensor are in motion, though. Both are in motion.
Well, okay. You want to handle that question, Ian?
Yeah. Well, see, it depends on which frame of reference you're using, Jerry. So you really need to stick to one for the moment, and then you can move to the other one. So from the point of view of an observer in the lab, looking at the disk spinning, the light source is in motion. That's right. However, we analyze its speed to be the same as if it were not in motion. In other words, it's moving. Well, I told you that Dufour and Prunier reflected the light beam all over the laboratory. So it must have been moving in the laboratory frame. It could not have had any additional velocity added to it, a la Ritz, so I say, because otherwise you wouldn't get it to reflect back from the walls of the laboratory and then find that there was no difference in the effect.
Well,
So it was moving in the ether, in the fixed ether, and the ether was not dragged by the disk. It's stationary.
Well, if Ritz's theory isn't correct, how does light propagate instead?
How does light propagate?
Yeah, I mean, if velocities don't add, like a la Ritz, if it doesn't work that way, how does it work?
Well, I could answer this way. I'll try to answer it in detail, but how does sound wave work? Okay, what happens? Think of what happens. If you bang a drum, it leads to a vibration of the molecules, and the molecules in the air will either be rarefied or they'll be contracted. They'll be compressed. And that's what impinges upon your eardrum and gives you the sound. Now, that sound goes through the air because the molecules are impinging upon the next molecules. But if you have a stationary drum, you're looking at it again from the outside, and you bang the drum, you get the velocity of sound, whatever it is, 1,100 feet per second. If you have the drum moving, you get exactly the same speed. It doesn't make any difference.
Yeah, that's what you're saying.
So yeah, I say the orthodox people say there's a difference in light because it doesn't have a medium, and its speed is constant, irrespective of the speed of the observer moving away or towards it. Now I say no, it's totally analogous. There's an ether which takes the place of the medium for the transmission of sound, or water waves or seismic waves, all the same, and you can analyze it in exactly the same way. And I say that people were misled by this quick fix of the Michelson-Morley experiment. Not only Einstein, but even the Lorentzian fix with the Fitzgerald contraction and all that. It's unnecessary because in the case of the Earth, the ether is actually dragged with the Earth. So it's as if you had a fixed ether, and you get very little effect. You do get a little effect, actually. Contrary to popular statements, the Michelson-Morley result is not absolutely zero. It's very, very small. But that's due to tidal locking of the ether, if you like, because owing to the sun and the moon. You can actually calculate this, and you get some very small value. But it's very, very small. It's approximately zero. Whereas if you do an experiment, you will pick up the revolution of the Earth, as Michelson and Gale did. Sorry, the rotation of the Earth. So I don't know if it convinced you. I don't want you to be polite, Jerry. I know you were very strong on this, and I don't know if you're convinced at all.
Well, the sound wave example, it's sort of tricky because it's constant, like if there's a moving sound source, it doesn't add to the velocity of the sound. It stays the same. However, though, it isn't constant in the same way that light is, because like where however fast you travel and you measure a light beam, allegedly it's the standard value. However, with sound, you could travel and measure the sound of the wave, and you would find that I mean, like if you were to well, it is sort of tricky. Now I'm kind of pondering this one over.
Well, with respect, Jerry, you've just quoted a common statement of the media, that it's been measured that however you travel, you measure the constant speed of light. That's incorrect. It doesn't
Oh,
matter how
I
you
didn't
said.
say that's true. I said supposedly. Well,
Yeah, but why suppose something that's incorrect?
no,
You're,
no,
you're not saying let's suppose.
I'm not assuming that it is true.
Okay.
Oh, okay, your sound example would seem to point more to the invariance of C rather than C isn't invariant.
You don't think sound speed is invariant. If I move towards a source of thunder, don't I get a greater speed of transmission between the thundercloud and myself?
What about how you can go faster than sound? Like you can like
Yeah,
you can I mean like the sonic boom for other.
that's right. When you break the sound barrier,
Yeah.
and you can go faster than light. Same thing. It's a bit
You're
more
not
difficult.
you're not changing the speed by going towards the thunder. You're reducing the length. So because you're in the frame, which is what you said earlier, that
Yeah.
it depends on the point of view.
Well, what's
Whether you're
true?
outside the frame or
Yeah,
inside the
I
frame.
mean, I get the same equations, but what's the correct analysis? So in other words, if I have a motor car going at 50 miles an hour from left to right, and I have another motor car going from right to left at 50 miles an hour, let's say on a road. Now, you might say, I say the relative speed of approach is 100 miles an hour. Well, if you said to me, it's not, it's only 50, the distance is being reduced. Well, if you want to put it that way, you can. But from a point of view of somebody in one of the motor cars, it's actually 100 miles an hour. And the force which is exerted in the case of a collision would be that due to 100 miles an hour. So he sees it as 100 miles an hour. And he doesn't see any distance being diminished. That's from the view of somebody outside the motor car. So there are two ways of looking at it. Depends which frame of reference you use.
The propagation
Yeah.
time is reduced too.
The propagation time is reduced. Yeah, that's the main thing.
This also happens with kinetic energy in terms of which frame you view it from, because it's not invariant. If you view it from outside the two cars approaching each other, because of the v squared, mv squared, it's not invariant with the point of view. So if you're in a car, there's a different. You can consider yourself stationary, maybe, and moving at constant velocity, and then the other one is coming towards you at twice the speed. So if you work out the total kinetic energy of what you're viewing, it comes out differently depending on which frame you're in. But it happens in Newtonian physics as well, and this is why ultimately I think that they end up with saying that kinetic energy is not conserved because they haven't worked out the frames properly, or it must all relate to absolute frames if energy is conserved.
I think it's conserved in the center of mass frame.
Yes, that's why they use the center of mass frame, but they don't actually
Correct.
explain why they use the center of mass frame.
I know, another one of those, yes.
Yeah. Anyway, okay.
I mean, it does lead to some conundrums about, you're saying the man in the first car says he's stationary, so he's going at a constant velocity, and the other car's approaching about 100 miles an hour, and you get the correct kinetic energy there. But if you're outside the frame and you're looking at these two cars, and you're just saying, well, it's just the distance which is either closing in or decreasing. Um, do you get the correct kinetic energy in the event of a collision? I suppose you have to, in some sense.
Well,
If
as
you use the center of mass frame, you're good to go.
yeah, your center of mass frame isn't.
But
Is
what is the
critical
center of
element.
mass in this case? Uh, Between the cars or between the observer outside the frame?
Uh,
Good question.
Between the cars is how it's normally handled. Because if the car's
Right,
a different mass, then you have to allow
right,
for that. Yeah.
right. That's a bit off topic here.
Yeah. Anyway,
We're,
I'm sorry for that, but as a link to Newtonian physics. Anyway. Okay.
Well,
right.
it's valid maybe to bring it up because I'm doing something that's very heterodox. I'm saying the ordinary type of Newtonian physics that we apply in dynamics and mechanics and all the rest can be applied to all these phenomena, which modern physics would say they're completely different arena altogether, and you cannot apply them. You need different transformations and so on of space and time.
Well, the modern physics has the luxury of abandoning the scientific method because your space time, where time is used as a coordinate in your frame of reference, um, if you're going to use it there, you can also use it to define laws of physics. So if you don't have, so you either have, you're going to go with space time and have no laws of physics, or you're going to go with three XYZ coordinates and have laws of physics. You can't use time in both places. That's abandoning the scientific method. It then is no longer an independent variable, and hence you get all these ridiculous assumptions.
Yeah, I know you raised that point with regard to James's paper yesterday, and well, it's something I'd have to look at in more detail. But but for my part, the transformations really arise from the basic parameters of space. We were talking about space, I suppose, the other week, um, and time, space and time. Um,
But you're not using Minkowski spacetime.
well,
You're
there's
using
another thing.
XYZ Cartesian coordinates,
I
and
am
time
and
is an
I'm not.
independent variable.
I am and I'm not actually, because I don't use it in the SRT sense, but it's actually, it probably predates Minkowski. If you substitute into the equations a value tau, that's the Greek tau, which is ICT, which is the Minkowski parameter, you'll get something like the sum of x1 squared plus x2 squared plus x3 squared plus x4 squared. X4 is not time. It's tau. It's ICT. Because otherwise you'd get x squared plus y squared plus z squared minus c squared t squared, as James showed yesterday. But anyway, if you do that, you can reduce the wave equation to something like quad squared psi, say psi is the value, equals zero. You're probably familiar with that, are you? The quad operator, which is basically the Laplacian minus 1 over c squared times the second differential with respect to time. Well, you can put that into a simple Laplace's equation is nabla squared psi equals naught. But if you use Minkowski coordinates, then you'll get the classical wave equation would be quad squared psi equals naught. I don't know if you follow what I'm saying.
Yeah,
So I don't rule it out altogether. That's what I'm
you're
saying.
talking about four vectors now.
Yeah, I am. Yeah, yeah,
Yeah, but in your case, it's just a notational convenience. It's not
yeah.
saying anything about a philosophical nature of space and time that Mikowski was gone about.
Yeah, that's correct. That is correct.
Yeah.
So, does maybe I've made a very big claim. Does this one experiment, the Sagnac experiment, show us so much. There are so many other things we could look at, but I'm claiming according to my analysis, it indicates that there's an ether. Well, Sagnac said that as well. Uh, it indicates that the Ritzian ballistic theory is not correct. Um, it it uh, it indicates that an object such as a spin will not have any influence on the local ether. Um,
You mentioned the dragging of ether. What evidence is there for that in your view?
well, the simplest answer I might give, Jim, would be that is the most straightforward explanation of the Michelson-Morley experiment. So, if the ether, the local ether, and I know you talk about Sue, Jim, there, local ether. I know I'm coming similar ideas. If the local ether on the Earth is dragged by the Earth on its revolution around the sun, well, then if you shine a ray of light in the direction of the motion of the Earth around the sun, or perpendicular there too, you'll get no difference because it's perfectly dragged. There are some other experiments actually which have been
No,
done as well.
don't forget the ECI. It's not that it's perfectly dragged, that
Yeah,
it
I did say
rotates
that
with the
earlier.
Earth. It's that it's a constant direction. So the Earth's rotation with respect to it, the ECI, is the small deviation that, well, it's the large deviation that Sagnac shows you, especially the Sagnac
That's why
GPS
we got the
correction.
Michelson-Gale effect. Yeah.
But if it's only 360 meters per second due to the Earth's rotation, Michelson-Morley can't detect that easily. And the
Not easily,
mirror-based
no.
can't at all because it's too insensitive. And that's why it seems to be, or is reported to be, null, except for the Brillet Hall, which
Yeah.
also I'd suggest that the GPS Sagnac correction is the best example that proves that it does not, the velocity of light does not depend on the velocity of the source, because all your satellites are traveling in all sorts of different directions and speeds when they emit pulse. But the answer is based on the location of the satellite when it emits the pulse. It has nothing to do with its velocity.
I've made that argument before with ballistic people, and they just shine it on, and
But it's so
they
obvious.
don't like that. Or I know it is, but ballistic people don't. The people
And that
believe in the
disproves
emission theory.
ballistic too. Yeah.
Yeah, I've had that argument many times with ballistic people and explained exactly what you explained to them, and it makes no.
And it's, it's linear, so it's really an exact contradiction of the inertial motion doesn't affect the speed of light, which
Well, GPS also clearly demonstrates that there's no correction for the velocity of the Earth around the sun. Okay,
right.
so obviously what GPS shows if you assume the ECI coordinates, the velocity is constant within the ECI coordinates.
Absolutely.
And that's also, I think, consistent with the Sagnac effect as well and the Michelson-Gale. What were you going to say, James?
Is the ECI taking account? Is it the actual center of mass of the Earth, or is it the center of mass of the Earth-Moon system? Does it vary with the?
That's a good question.
Because I've never.
I think the whole thing is set up based on the geometric center of the Earth.
So it's
but
yeah.
because
the point is that it doesn't rotate with the Earth; it's got a constant direction.
Yeah.
I want to point something out to you that I learned on the YouTube is that according to GPS, Greenwich, the line that they have at the Greenwich Observatory, which is the 0 of longitude, is not the zero of longitude for GPS.
No.
So they have a different coordinate system, and their center of longitude is Skaggsville, Maryland, which is where Johns Hopkins APL is located, which is essentially where the basic work that results in GPS derives from.
Well, it perhaps shows the political influence on things like that about what should be your standard or your 0 point.
No, they actually have the zero near Greenwich, but it's not the same as the Greenwich zero.
Yeah.
Okay.
Yeah, I thought
Which
I read that somewhere indeed. Yeah.
Right. So what that shows you is that the the coordinate system, the way they're setting it up, that's based on their measurements. Okay, where they've set themselves as the 0 point for their geoid, but when they it's kind of I don't know the details of it, but I think it's interesting to note. So the issue is they have a model Earth, they have a geodetic model of the Earth, but it's it's based on their being the reference point. Does that make sense to you?
Is this anything to do with the fact that the Earth isn't a perfect sphere?
I think it does. I'm not really sure how they come up with their calculations. So what I say is just for point of reference. I think this whole issue is very complicated when you really get down to the nuts and bolts of it. And all we really understand are kind of the general outlines. And the general outline is the ECI, the velocity of light in the ECI frame, which is Earth-centered inertial frame, is constant.
Out to where the sun takes over.
How far
At
does the
one
ECI
point,
frame extend, though?
sorry.
How far does the
In terms
ECI
of
frame
it being
extend, though?
a reference frame for EM radiation, it's about to 1 million kilometers. And then the sun's local ether becomes the reference frame.
Why would C be invariant within the Earth's sphere of gravity, though?
It's a philosophical question, I suppose.
As opposed to outer space. I'm sorry, what'd you say?
If there's a medium, well,
Yeah.
and it's shown by GPS essentially that works.
Well, I mean, at what
Just
point
always
is
think of it in
is
terms of the
invariant?
analogy with, say, sound. Imagine that you have a gas around some sort of object, spherical object, and the speed that would determine the speed. And then if you have some other object which is remote from that, it would have another gas around it, and within that gas, it would have a different speed. That would be the way I would look at it in terms of the ether, which determines the local speed of
Well, I
electromagnetic.
mean, is the change gradual when you get to a certain point? Is it suddenly invariant and then it's non-invariant?
I don't like using the word invariant. You keep on using that because I think it's
constant. I
misleading,
mean,
Jerry. It's
I
just
mean,
defined by the medium. Yeah. Okay. If you're in different ethers, I don't suppose there could be a sharp dividing line. There would have to be some, um, you know, variation,
Transition zone.
regression, transition. Yeah.
Well,
Uh,
there's a problem that's always been said about the dragged ether, and that is the fact that it complicates the stellar aberration. And Lorenz did a calculation that the dragging effect would have to decrease in some sort of exponential wave for it not to become an instability.
Yeah, but if you assume that the alteration of the angle occurs at the boundary between the Earth's local ether and the sun's local ether, that solves it.
So I
Right,
think
so
Jim and I have similar ideas, although we express them in quite different ways. The
so
way the way I express it is I've done calculations which seem to indicate that wherever the radiation originates, it actually maintains that system. There's a memory in it, and that's why, for example, when you have something originating from outer space. It doesn't matter the medium. You could put it through a water-filled telescope, as Airy did, or you could put it through air. You don't get any difference because it maintains its original system. And basically, that seems crazy to think about. But basically, at the transition between any of these ethers, you would get a variation because of the different speeds, but that would be cancelled out. It's related to the sine of the angle actually, and that's cancelled out by Snell's law, which gives you the
Basically, a Fresnel dragging in the yeah.
yeah. It's so
Sort
I
of
know
thing.
at first glance that I think actually that's responsible for maybe the mess we're in, and that started at the beginning of the 20th century. Michelson himself said, he says, I've invented a monster. They were just, telling everything. It seemed to contradict itself. Okay, well, maybe there's a drag, but then yeah, simplistic analysis said it couldn't be because of aberration. So what do? We cannot reconcile the two. We better develop a new explanation
Mm.
altogether.
Well, I think this basically illustrates that there's a big giant muddle, and we don't know how to get out of the muddle. And there's a lot of different aspects of the muddle. There's the muddle of what is time changing. There's, that's the whole problem of time changing. And Einstein connected that to the speed of light is invariant principle to derive the Lorentz transformation. And there doesn't seem to be any real understanding of the Lorentz transformation mathematically. That's not being used correctly, in my opinion. And then now you've got all these different transformations, Tangleriani, Solari, and it's trying to get into it. And we still don't understand whether the velocity of light, what determines the velocity of light correctly, whether it's a ballistic theory or special relativity. I think special relativity and ballistic theory are both wrong. That's your conclusion.
That's my
I think,
conclusion. Yeah.
right.
I would
And
agree
I
with that.
think, and so we can sort of, I think we've sort of solved that part of the problem about the velocity of light and what determines the velocity of light. But then the other data, which you just mentioned about the aberration of light, seems to be inconsistent with that particular conclusion. So we still have all these contradictions. The evidence is, if you try to make all the evidence and all the experiments consistent with one theory, it turns out you can't do it. So it's still a muddle. Does that sound correct to you, Ian?
It does, Harry. Yes. And sometimes they quote what from Alice in Wonderland, that bit where uh, the man wants to find a way to dye his whiskers green, but then carry so large a fan that they could not be seen. So everything seems to be, you get one idea and then something else contradicts it. And so maybe there's an explanation, or one can almost understand how they arrived at such crazy ideas 120 years ago because of the confusion that you've referred to, Harry. But I think by looking at it in a more calm and deliberated way, and not jumping to conclusions, which I think they've done, by saying space is not what we thought it was, and so on. You can get a solution. There are still some little things to pick up, but I think you can get a solution. I'm trying anyway to move people very slowly in that direction.
Well,
Well,
thank
that
you very
seems like a
much. Yeah,
good summary of your talk.
yeah.
Well, thank you. Well, it's great having the opportunity to tease my ideas out. I mean, I enjoyed having these non-technical people just respond to me, but I enjoy even more having you, my peers, respond to me with all your different ideas. And everything that you've all said today has been very relevant, which I would have been surprised had it not been. So, we need to look at this, and I hope it's helped you as well. You even said, Harry, that some of the ideas were slightly tangential to what you had seen, and maybe again having the recording. I don't know. Sometimes people say if I'm right, the truth will out. Maybe.
Well, the problem as I see it is that mainstream sort of decided on a particular correct um, Einstein's theory is correct and his postulates are correct. And it seems that, they're really resistant to admitting that that's not the case. And GPS is a good example of that, where they say GPS proves relativity. And then other people, look at it and say, we don't understand how that can be. They also do the same type of thing with the Sagnac experiment, where they say it's perfectly consistent with relativity. But then it looks like, oh, wait a minute, we have to use general relativity.
Yeah, I didn't go into that, but that's true. You had people like Langevin and others and Bourne who did that. But it's actually interesting as well why they don't introduce this into undergraduate courses. I mean, you might imagine they say, okay, they might come across this and they'll think that what we've been telling them is incorrect. So we'll show them, here's the Sagnac effect, and I'm going to show you why it is consistent with special relativity, and don't believe anything to the contrary. They're afraid to do that. It's not even introduced into undergraduate courses.
I don't think they can do it. That's the point.
A
That's
question
pretty
for
true.
Ian.
But Wikipedia tries to do it. And I dare
Yeah, I
say
know.
AI, which I haven't used today, if you plug it into AI, they'll try with all these ridiculous explanations.
Well, I think what
Lorentz
happens is,
transform the Lorentz transformation is a negligible effect on the GPS Sagnac
That's
correction.
correct. Yeah, that's correct.
It's
A
negligible.
question for Ian. There's
And
been some talk about local ethers, with respect to the Earth or the sun was mentioned here today. What is your view about an absolute reference frame?
Right. Well, that's the big question, Jim. But thank you for it all the same. Um, I-
excuse me,
m-
before you continue, what do you
yeah.
mean by absolute reference frame?
Well, that's a good question. That would be where we could determine if an object is in motion or not. Binary mechanics defines that precisely with equations. So I'll return the question back to Ian
Yeah.
for his response.
Okay. I know there is an uncertainty there, but insofar as I might try to interpret it, I would say I sometimes use this phrase relative to the universe as a whole. It's a bit of a kicking for touch. I don't say absolute frame, but I do conceive of there being, a space which the universe occupies. And however, I don't equate an ether with an absolute frame. You see, I talk about the local ether as we've been talking about, and the ether is moving. The local ether of the Earth, which is moving with the ECI frame, is moving relative to the universe at large. It's a bit of a mathematical concept.
Yeah, that's why I asked the question, if your thinking goes beyond that to something like a more absolute frame. Because in all of these relative frames, we really can't say whether an object is in fact moving.
That's right. But
Well, I mean,
In fact, isn't Newton's first law basically that like an object will keep moving in a particular direction, its motion vector, if you will, for forever. Of course, if you're riding on that object, the object's not moving at all
yeah,
in that frame.
yeah.
well, we can measure objects relative to other objects, though, such as a car going 55 miles an hour. It's relative to the road. I mean, many practical purposes that way, even if there is an ultimate frame.
But I mean, he's saying is one of those frames ultimate. But what we can do is we can measure motion, absolute motion, if you want to use the word, uh, which is accelerated. So accelerated motion or what amounts to the same thing, motion in a nonlinear form is accelerated. That can be measured relative to the universe at large, to use the words I use. You can measure that.
Thank you.
And follows from Newton's law
Hey,
as well. Yeah.
I want to reiterate what I said when I was talking about space, relative and absolute space. What Newton said was that there's an absolute space, which he defined it. Okay, and he defined it as the sensorium of God, supposedly, according to Clarke. But he then also said there's relative space, which is a copy of absolute space, and it's relative space that moves. So the Earth is relative space. So the ECI is a relative copy of absolute space. Do you understand that idea?
Well, it seems to be a theological sort of interpretation of what one might describe loosely. I do understand it. It's just putting a theological construct on it.
We
Well,
need
I
to
think
be
the
able
point,
to distinguish between geometrical concept of space and a physical ether for propagating EM waves and possibly gravity. They're not necessarily the same thing, but people talk about them as if they were.
I'm not sure I quite understand that, Jim. Could you read?
Well, if there's a medium, if it's a substance that fills the geometrical space, it's a different idea. It's not a
Well,
space, it's a physical thing.
that's
So is it that when we look at books on special relativity, they start by saying they used